Okay, it's 3:01. We're going to go ahead and get started. Good afternoon, everyone. My name is Jamie Kostelnik. I'm a member of the small committee led by Matt Thomas that organizes the Landslide Hazard Seminar Series. Before we get started with this afternoon's presentation, I'd like to take a minute to acknowledge that today marks our 100th seminar speaker, and mostly to recognize Matt's effort in making this happen. Matt started the seminar in February 2020. Originally, these were internal, in-person presentations by USGS and Colorado School of Mines scientists. Of course, shortly after the seminar was started, COVID ceased in-person meetings and we all transitioned to the virtual world. Matt recognized the utility of virtual platforms to expand the breadth of audience and presenters. Today, this platform brings together landslide researchers, academics, students, applied scientists, and others to share their work in a long format. Today marks 100 seminars organized, arranged, and facilitated mostly by Matt. Along the way, we've had a few guest facilitators. To date, the seminar averages over 70 online viewers, and we've had over 100 YouTube views since we started posting presentations in July of 2021. Some other fun facts about the seminar. We've had talks from 16 state geologic surveys highlighting their landslide-related work and programs. Our farthest presenters were from 7,500 miles away in New Zealand, and we've had viewers from as far away as Taiwan, Sri Lanka, El Salvador, and Canada. So let's all give Matt some virtual kudos for bringing landslide science and the USGS landslide hazard program to a global audience. So thanks, Matt, for all your hard work to make this happen. And I'll also mention, if there are any folks on the call that are in or near Golden, come out and join us at Golden City Brewery this afternoon following today's seminar to celebrate. Now I'll turn it over to Matt to introduce today's speaker.
Hey, thank you very much for those kind words, Jamie. The only thing I'll say with that is it's been a pleasure to do this, and I'm so glad I had the help of Stephen and Jamie and others who have covered while I've been out of town. I think the one big lesson I've taken away from this exercise is that our community, landslide community, is a lot bigger than I initially thought and realized. And so with the 100 or so speakers we've had, it's been a pleasure to get to know each of those people leading up to their talks. So thank you so much for your presentations, and thank you for being a good audience. I'm going to go ahead and get things kicked off for today. My name, as you heard, was Matt Thomas, and you're tuning into the USGS Landslide Hazard Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of Thad's presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted and your camera is off if you're not intending to speak. It's my pleasure to introduce Thad Waskowitz today. Thad leads Stantec's U.S. Geohazards and Geomorphology Group within the Environmental Services Division. He's a subject matter expert in debris flows, debris flow modeling, alluvial fans, and hill slope channel coupling. He applies high-resolution topographic data collection, processing, mapping, and analyses, as well as 2D modeling to assess and manage environmental hazards. And he also brings extensive international experience to this work. So, Thad, thank you so much for joining us today. I'll let you take it away.
Perfect. Thanks, Matt, and thanks, Jamie and Stephen, for inviting me. So today I'd like to present a little bit of work that we've done on post-wildfire debris flow and large woody debris transport modeling. In this case, from the North Complex fire leading into Lake Oroville in California. The work is part of a project we did here at Stantec for the California Department of Water Resources, task order number 23, that was large woody debris modeling for Lake Oroville. So in this particular watershed in Lake Oroville, it's experienced a fairly dramatic wildfire history that throughout the past has been dotted by numerous wildfires. But more recently, we've seen some of the two of the largest wildfires in the state of California, or two of the top 10, I should say, wildfires in the state of California to occur within this watershed. The North Complex fire, which occurred in 2020, and then the Dixie fire, which occurred in 2021, both of these burned in excess of 485,000 hectares of land within the watershed. And you can see that sort of mapped out here in these set of diagrams. Obviously, this is concerning to DWR for many different reasons, but one of them is that they were particularly concerned about the potential for large woody debris from these burned areas entering in to Lake Oroville. Obviously, a variety of impacts that can result from that. So we were asked to investigate how that large woody debris might be entrained and then ultimately mobilized from watersheds in the Lake Oroville, or smaller watersheds in the Lake Oroville watershed, to Lake Oroville itself. And so we came up with an approach that combined debris flow modeling, hydrodynamic modeling, as well as large woody debris transport modeling to look at from small and medium watersheds how large woody debris might be moved and how much of it would make its way to Lake Oroville itself. So a little bit of background on this. When you look at the literature surrounding large woody debris transport and wildfires, there's an overarching theme in that literature that suggests that large woody debris transport is going to increase or at least be larger than those areas that are non-burned. This is can be relatively complex though, because in some cases wildfires and varying intensities can either increase or decrease the size and volume of large woody debris that's available to transport. And then the magnitudes and frequencies of those transports, that large woody debris transport, is often thought to be enhanced by the conditions brought about by wildfires, where you're seeing the potential for higher magnitude flooding, and in steeper areas, the potential for debris flow, which has greater capabilities to transport that large woody debris. And so debris flows themselves have been looked at in terms of large woody debris, and they tend to very easily mobilize that large woody debris that's in the extent of the flow pathways. And in some cases, that's being transported all the way out of the system or along the entire runout of the debris flow. In some cases, that runout is also inhibited within the watershed, or in other cases, we might actually see just deposition taking place of the large woody debris via debris flows within the watershed. So other things that are brought about by wildfires are also a series of secondary processes that can also contribute or add sort of more large woody debris into the system. After these wildfires, we can see various mass wastings events, from landslides to bank collapse, that lead to standing woody debris or even down debris entering into the system. Wind throw obviously plays a big role in this as well. Different root weakening as well as disease can also lead to further inputs that then increase the potential for more large woody debris moving out via debris flows. We've also seen within these systems that large woody debris can be deposited and store quite a bit of sediment, and that sediment in some cases may be as much as the material that's deposited within the alluvial fans themselves at the end of these streams. And when we look at the literature, there's actually been a very limited amount of research that's looked at using debris flow models to transport large woody debris. When we look at the other end of the spectrum, though, as that large woody debris enters into the main trunk streams within areas, there's actually been many attempts to model large woody debris transport, and in many cases early on, that numerical modeling was also combined with sort of flume experiments to potentially examine a variety of different things from sort of the force or balances between the wood and the water itself, or simulating bed deformation by large woody debris, and in other cases by examining multiple local forces on cylindrical wood. Another approach, and the approach that we've kind of taken here, is to attempt to simulate the spatial and temporal transport across a defined space at the resolution of the individual trees. And that's kind of how we approach this idea of entrainment and fate, was to use this spatial and temporal transport, and I'll explain this in more detail. So as I mentioned, we were focusing on the North Complex fire here. The North Complex fire was actually started as a series of fires from lightning strikes in August of 2020. Those smaller fires eventually coalesced to form, the larger fire. And that fire was contained roughly about 4 months after it initially started. During that period of time, it burned about 130,000 hectares, and we saw 16 fatalities and over 2,300 structures that were either damaged or destroyed by this fire. And as I mentioned earlier, this is the seventh largest fire in the state of California as of 2022. So in this, we had a limited window to turn something around to DWR. And so we tried to scope this work in a way that we were working under the premise that medium and small watersheds would be the largest contributors of LWD to the middle fork of the Feather River. And so we focused on this initially. Having gone through this, I think that there needs to be more assessment of this, but we've kind of rolled with this given the time and the constraints that we had. We took the watershed sizes and the likelihood of debris flow occurrence as a way to gauge which sites to pick. We randomly selected sites that had a debris flow likelihood from the USGS landslide hazard assessment of 83% likelihood or higher in our selection, and we ended up looking at 8 medium-sized watersheds and 5 small watersheds, and these were defined small and large based upon the population that occurred within the fire. So it's a local, medium, and small watershed size. So the first step in this was to conduct the large woody debris mapping. And we define large woody debris here based upon Kramer and Wall 2017. And as a caveat, we're only focusing on large woody debris that was on the ground. So this doesn't take into account for that standing woody debris that was left in the area. So that's one caveat to our study. To get at mapping some of this large woody debris that was on the ground, we decided to use a fairly simple approach here, where we took a digital surface model, which was the segmented part of a LiDAR point cloud that had unspecified points. We found that's where, in the segmentation of the point cloud, where a lot of this large woody debris that was on the ground was left behind. And what we did was then also developed a bare earth DEM from the classified data, and we subtracted the bare earth DEM from the digital surface model to produce a difference model that then we went and classified based upon elevation what we thought would be the approximate heights of the large woody debris that would be on the ground, and typically that ranged between 12 centimeters to 1.3 meters, depending upon the watershed and the tree species that were associated with that. And so what you see on the right-hand side here is the remnants of that different surface and the classification that shows some of the large woody debris for a section of one of the watersheds that we were able to pull out. This allowed us to determine if the large woody debris fell within the pathway of the debris flows that we modeled, as well as gave us an opportunity to measure the dimensions of the large woody debris. And in some cases where the results were a little bit ambiguous, we'd also incorporate the aerial imagery to help us define what the extent of that was. But depending upon when the imagery was flown, that also can be a little bit ambiguous as well. The data were still noisy, but for the most part, we were able to pick out the large woody debris within the watersheds. So from our debris flow modeling side, we used a modeling software called Debris Flow Predictor. Debris Flow Predictor is a 2D agent-based landslide simulation model that models debris flows, as you can see from the image here on the right, from where they initiate to where they run out and deposit. So we're measuring the complex debris flow behavior from initiation to its final fate within these. So along the pathways, we're predicting runout, scour, deposition based on a series of interactions between the agents and the slope, as well as the agents and each other. The agents are choosing their pathways down through these areas based upon those interactions, and they're scouring, depositing sediment until that sediment balance is zero. The information that's feeding this are a variety of different things, but at the base, we're also using a 5-meter digital elevation model that we're initiating from. I'm not going into all the details, but the details of that are described in this Guthrie and Bayfus article that's cited here. So with regard to the debris flow initiation, in this case, we were looking at our initiations and using again the USGS's land debris flow hazard assessment, where we took stream segments that were longer than about 0.4 kilometers and had an 80% probability or greater of having a debris flow occur at rainfall intensities of 24 millimeters an hour for the 15-minute rainfall intensity. We went through and used those as a way to establish the number of points that we should be initiating here. And then within there, we also looked at placing these points in areas that had a high burn severity based upon the bark maps here, as well as slopes greater than 30 degrees. And in this case, when we look at the rainfall intensity for this area, the rainfall intensity has a less than, or with the 24 millimeter per hour, that's a less than 1 year return interval, which if you've read the article that we produced from this, that was my fault. I put the wrong return interval into the article, and I'm working on getting that changed, but this is the right output from that. So the debris flow models themselves were calibrated locally, and those local conditions were looking at a variety of different things, but in cases identifying fans where we could. In this case, some of the fans were from more recent smaller events, and we had to extrapolate out that from there to get some idea of the extents that we should be modeling to and the depths that we should be modeling to. We also considered the availability of material in on the slopes themselves, as well as within the channels that were tributaries to the middle fork of the Feather River here. Most of what we saw was that these deposits were relatively shallow in many of these steeper areas. And so when we initiated landslides, we were typically initiating for landslides that had a relatively shallow initiation depth. In the time that we were modeling this as well, the debris flows in the Dixie Fire occurred in another section of the watershed. And so just to see how our model calibration performed, we actually applied the same sort of parameters to flows coming out of Opapi Creek and Murphy Creek, which were two known debris flow events. You can see here on the image from the left-hand side, the Caltrans. And Matt's actually done some work on the rainfall intensities here as well. Overall, we thought the models performed pretty well in terms of depositing in areas where we'd expect at depths that were similar to what we estimated in these areas. The model also eroded in areas where the debris flows eroded on the downside of the road prisms here, and then extended out to roughly about the same extents as what we could see from the imagery that we could acquire for this. So one of the caveats of doing the debris flow modeling here is that debris flow predictor is not a model that either identifies or specifically entrains large woody debris as it is transporting material down through here. The large woody debris in this case is assumed to be entrained along the debris flow pathway as it's encountered. I searched, but I couldn't find any sort of agreed upon way to model this. So we just assumed that if a third of the length of the large woody debris was within the debris flow pathway, that debris flow would be entrained. And so in this case, the entrainment, we didn't have a way to really gauge if some of that material would be deposited, and because we weren't looking at or incorporating the standing trees, we just assumed that if it was being entrained, it was going to be transported to the trunk stream in this particular case. One of the things that we noticed is that in the trees that were within the flow pathways, very few of these actually had root wads associated with them. And the reason I make this statement is because those root wads become important in terms of modeling subsequently the transport in the hydrodynamic, dynamic, and large woody debris transport models. So what we did was, because we couldn't entrain the large woody debris in the debris flows, we ended up actually coming up with a way to randomly place the large woody debris on the alluvial fans. And so based upon our own experience and what we could see from things that we tracked within the literature, is that a large amount of the woody debris, as you can see in the map here from the 2020 article, a lot of that is pushed out to the lateral extents. There's not really a huge amount that's stored, and we've seen this in other locations as well. And so when we're thinking about a way of placing this within the context of the fans, what we did was we came up with a sort of, again, another assumption, but one that was based upon these observations, that we would randomly place a larger percentage of the large woody debris in that toe and lateral extent areas. So in this case, 70% of the material would be placed here, and then the remaining 30% would be placed in the center as well as being pushed out to the edge. So again, an underlying assumption that we kind of pushed forward. This is the final plot of what this particular site looked like, with the random woody debris being placed at this particular site. And so each one of these has a coordinate and a series of other data that would be associated with it that then was exported out to be placed into the hydrodynamic model. So our modeling results produce this from the various watersheds, where what we found was we transported roughly about a little over 1,000 large woody debris units within the total example that we had done. The medium basins produced a larger amount of these than the smaller basins, which wasn't completely unexpected, but I think the magnitude of it was a little bit more given what we had originally gone in. And you can also see here the different debris flow volumes that we put out as in comparison to the large woody debris volumes here in these basins. So having gotten the wood out to the middle fork of the Feather River, the next process was to produce the large woody debris transport modeling. And here we used HEC-RAS as the model because there was an existing HEC-RAS model that DWR had produced for the Frenchman Dam model, which is cited down below. In this, because we were dealing with fairly complex flow and channel geometries, we actually refined the original mesh and dialed that down to a finer resolution to be able to capture some of the complexity in the hydrodynamics as well as the channel geometry. And I'll show you an example of this in a second. The model was driven by discharge upstream. The domain extended beyond the 13 watersheds that we investigated, and there was a constant outflow at the reservoir in the initial model. So this is an example of where we refined the mesh in these areas of where we had really complex flow. So the mesh resolution was refined down to 5 meters through these areas to deal with some of the complexity and better map some of the transport. So the large woody debris transport modeling hydrologic events were a series of return intervals of or recurrence intervals, excuse me, where we looked at the 1 year, 2 year, 5 year, 25 year, 50 year, and 100 year and 500 year flood events to see how they would impact the transport of large woody debris throughout the system. So our large woody debris transport model is used a combination of the hydrodynamic results from the 2D HEC-RAS, largely incorporating flow depth and velocity vectors for the most part. The model that we used to transport the large woody debris was LWD SIM-R, which was developed in 2016. We found that the model actually ran fairly slowly, and so we actually took the original code and then produced a Python code for this that we call PyLWD Sim, and incorporated that with the 2D HEC-RAS modeling. And in this case, when we model, please note that the LWD itself, its influence on the flow is neglected within the model. So ultimately, the model that we designed here was using a sort of a two-nested loop where the function of the outer loop was to load the hydrodynamic results in terms of things, in terms of the flow depths and velocity vectors at predefined output time steps, and then incorporate that into our Pi LWD sim model. And then the function of the inner loop was to actually calculate the transport processes of the LWD at much finer time steps that was allowed us to sort of resolve the transport processes ongoing for each one of the individual pieces of large woody debris. So as I mentioned, the model inputs here were actually the XY coordinates, or the point values of all of the large woody debris that we transported to the alluvial fans. And so those had a starting coordinate, and then the other information that you see here that was associated with those, that was ingested into the model to take into account for the transport of each individual piece of large woody debris. The model outputs at any particular time stamp we're producing location, the status of the wood, different characteristics, as well as the hydrodynamics. And each piece of the wood we could view in at every 5 time steps to really allow a sort of detailed understanding of the temporal transport dynamics. And so ultimately, this is how we were looking at the paths as well as the fate of the large woody debris, and sort of some examples of, you know, through the various stages of transport here where some of the large woody debris ended up. So in this process as well, we came up with a way to look at both large woody debris as it was just being transported with no sort of jam scenario in the system versus one that we adjusted based upon removing large woody debris that had a length greater than the channel cross section width. This kind of is a little bit overkill because in many cases there's not a huge amount of large woody debris that's stored within the system here in terms of jams and things along these lines, but we wanted to kind of take a look at this and see sort of what impacts this might have. So this was our way for adjusting, you know, wood getting jammed within the system. So in doing the large woody debris temporal dynamics, what we found was that you know, wood started to move at fairly quickly within this modeling process. And you can see here in this diagram, the green represents trees that are being mobilized, or the volume of trees being mobilized, and the browns here represent deposition of trees. So the LWD mobilizes fairly early on in the time steps here, and there's also some of that material being deposited as well at the same time as it encounters the banks. As the discharge increases, as you would expect, you see increases in the large woody debris that's mobilized. And then as the hydrograph begins to sort of come down here, that woody debris is being deposited out. The mobilized large woody debris is eventually making its way down to all the way to Lake Oroville, and I'll explain what those totals look like in a second. So that transport pathway tends to be concentrated along the main channel. What we found is because of the narrowness of the canyon areas that we were working in, there tends to be a flow constriction in these areas that continue to push portions of that large woody debris down through the main section of the channel. As that large woody debris enters into the reservoir, we start to see a little bit of that expand out based upon the dynamics of the reservoir itself, and eventually flow all the way here to the emergency spillway and to the flood control outlets that were operating during the modeling. Now, this doesn't take into account for any wind that might be occurring on the lake, so you're largely just seeing current-driven pathways of where the large woody debris moved. In this case, the volumes of large woody debris that moved within the lake itself. Not all of the large woody debris made it to the reservoir. Some of that large woody debris was deposited in areas where you would typically expect wood to be, and in areas where we saw from our analysis of aerial imagery. So areas like where we had bars that split, a section of the channel that expanded outwards, that would have potentially reduced some of that flow. Other roughness factors as well that would have caused deposition. Now, in terms of the total transport ratio, we did this adjusted, non-adjusted, where we looked at all of the large woody debris and then taking out in the blue here some of this that would potentially have jammed. And you can see the amount or the transport ratio for the various return intervals here, which is not unexpected that we see this sort of rise in this. When we look at the transport rates based upon the individual watersheds, those transport rates vary quite a bit. So depending upon their connectivity and where the large woody debris was deposited on the alluvial fans, that impacted to some extent the amount of material that was being transported from each one of these watersheds to Lake Oroville itself. So those transport ratios, we wanted to kind of get a sense of how well those were performing. And we did a comparison to past large woody debris that was removed by DWR. And DWR typically has to remove large woody debris annually, and they typically gather it up and store it in a particular area. Unfortunately, the storm intensities were not recorded for the large woody debris piles that we were given access to. This one that's here in the image was roughly about, when they took this wood out, was roughly about 10 hectares in dimension and roughly about a height of 1.2 meters. So we assumed a packing ratio of 0.25. For the wood in this pile, and estimated a volume of about 30,837 cubic meters. And when we compare that to our results, we see that falls within the range of our 2 to 5 year return intervals, which is probably fairly realistic. So we're at least in the ballpark. We're working with DWR to try and get more information about this this year to help refine and calibrate this model in a little bit more detail so that we can look at specific events. But nonetheless, we're within the ballpark of what has been at least collected from past events. So in summation, what we saw here was that large woody debris transport modeling shows that floods that range from, say, 25-year to 100-year recurrence event can transport a fairly significant amount of material from these alluvial fans down to Lake Oroville. So in the 25-year to 100-year, we saw roughly about a transport ratio of about 34 to 39%. Obviously, as we increase, that gets a little bit higher, upwards of say 40 to closer to 50% transport ratio from these areas. Some of the watersheds had a higher connectivity to the middle fork of the Feather River, and their transport ratios were much higher, upwards of say 60 to 80% of the large woody debris that occurred on the alluvial fans were transported all the way through the system to Lake Oroville itself. The entrained large woody debris, as I mentioned earlier, if it wasn't carried to the reservoir, it was being deposited in areas where you would typically expect it to occur, where the hydrodynamics are changing enough to have that large woody debris settle out, or it's interacting with various roughness components that are in there, in the system, excuse me. The post-wildfire debris flows do have a potential to contribute a large amount of sediment. On average, we estimated that there was around almost 240,000 cubic meters of sediment. Even if you cut that in half based upon France's numbers, it's still a significant amount of material that is being transported through the system, and not much of that material is surviving, as you can see from the image here. So there is fairly efficient transport of that material down through the system. Excuse me. So I'll finish there.